Hi, this is Dr. Y.S. Rao. In this session, we will discuss some other output components, that is, motors. So far, we have discussed about LEDs, LCDs, buzzer, which are the indirect way of indicating what is happening inside the CPU. So, similarly, now we will see through some motion whatever is the program you have written, whatever your algorithm may be, those variables, those numbers, those signals, how they are converted into some displacement, some action. So, as far as the robot which we are currently using, you have two motors here. You can see this fellow, white one. There is one motor on your left side, there is another motor on the right side, which are fixed to this printed circuit board with the help of four screws, two screws on vertical, two screws on the below this motor horizontally. So this 2 plus 2, 4 screws. And then after that, you have fixed, this is a detachable wheel. You have fixed this to the DC motor. So these two DC motors, the two windings you can see across this capacitor is connected to the PCB. One here, which has a direction, the black male female connector. It is another connector here, male female black colored, is connected here. So both the motors are working on 5 volts DC motors. As far as this interface is concerned, on the board, the motors are connected. As you can see, left motor forward action takes place with the help of port C PC1. Left motor backward action takes place because of port C PC0, and the speed of the motor is controlled, what is called, with the help of technique called pulse width modulation techniques through PD5. Similarly, the right motor forward direction is controlled by PC2. Right motor backward direction is controlled by PC3, and again the speed of the right motor is controlled by using PWM technique through PD4. So in short, we have used PC0, PC1, PC2, PC3 and PD4, PD5. So that means, as you can see on your CPU, 40 pin CPU, there are 4 ports are there, PA0 to PA7, PB0 to PB7, PC0 to PC7, PD0 to PD7. So here what we have used is PC0, that means pin number 22, PC1, PC2, PC3, right? These are the IO lines we have used for connecting the motor with the help of a motor driver circuit, and also port D. So port D is here. In port D, we have used PD4 and PD5. That is, PD4 is pin number 18, PD5 is pin number 19, where they have some special feature which is mentioned in the bracket called OC1A and OC1B. They are nothing but output compare, timer 1A and timer 1B, which are meant for generation of a pulse width modulation. So we will see what do you mean by pulse width modulation, how it will control the speed of the motor. All right. So before we talk about the interfacing and programming, first let us try to understand what is the need of the motor in this system, in robotic system. In robots, they are not just they are not just meant for making a talk or a recognition of the objects. right? There also has to be some action, some physical action. The way humans are having physical action where we can talk, we can walk, we can move, we can lift, right? All these things we can do it with the help of our various parts of our body like arms, legs, and so on. So similarly, if you want to do the same things in a robotic systems, right, in a machine, so the machine, how will you do the same thing? For example, take one hand. One hand means now you should have a one rotation here, like you have wrist, you have ankle, you have shoulder, right? You have fingers. So similarly, in a machine also, you would like to have a rotation, horizontal rotation here. Then there is a another vertical rotation here where you can bend forward and backward. Here you can rotate 360 degrees. And again, like a wrist type of thing here, another horizontal rotation. Then there is a another vertical rotation here to rotate the arm. Here again the grip you want to rotate, right? And the gripper itself if you want to rotate. So in one hand itself, you will find one. And second thing is by how many degrees that rotation can takes place. Is it 360 degrees? Is it 180 degrees? It's a 90 degrees. And by what step? It's a continuous rotation or maybe a step by step manner that rotation is happening. Okay, so these things, freedom of access, can be achieved with the help of, as you can see, some motors, right? Some joints, some gears, some screws, threaded screws, like that. So you have to realize this freedom of access with the help of by making appropriate joints by either metal sheets or a plastic sheets or some fiber, whatever, whichever is the amount of load which you would like to lift. All right, so based on the load and based on your freedom of access and the number of degrees of freedom of access you would like to achieve, accordingly you have to design the mechanical things. And then you can place the appropriate motors in order to achieve this freedom of access. All right, so how to rotate, how to achieve that freedom of access, and what is the displacement and what is the amount of load it can lift, it can move, it can pick, it can place. What is the minimum, right, displacement it can achieve? What is the maximum load it can lift? And so on. So these are all the questions which will arise. So you have to find a right motor in order to achieve this. What are the types of motors? There you can achieve these things. A classical DC motor. This is what generally right now we are using on QU board. But when you go to industry, probably you prefer to have a geared DC motor where we will see a lot of inside the entire rotation is reduced by with the help of some gears so that you can achieve the highest possible torque or pneumatic and hydraulic. So what's the major difference? In case of a DC motors, the entire load is lifted by some rotational object, that is your armature. So this armature is lifting that load with the help of the current. So whatever is the amount of current which you have passing through this motor, that electrical energy is converted into mechanical energy. That's what it takes place here. However, in a pneumatic, as the name says, a pneumatic means air pressure or hydraulic. Hydraulic means it's a some fluid, right? Fluid pressure. So with the help of some pneumatic, means if you have a some compressor, that compressor compressed air, that pressure if you are using for some displacement, some rotation, then we call it as a pneumatic control. Or if you are using some liquids, right, some oil, which is in a compressed form, like you might have seen in four wheelers, two wheelers, railways, the opening or closing the doors, or in cranes, right, JCB machines. They're all hydraulic controlled. A compressed the oil, whenever it is released, some displacement is happening. So that controlling the oil, controlling the air pressure is done with the help of some actuators. Actuator is again it's a coil, it's an inductor which is converting the current into some magnetic field. Some displacement takes place. However, here the displacement, the other type of motors, you can also use an industrial servo motor or stepper motors. So there is a difference in principle of working. In case of a servo motor, the principle of working we will discuss in the subsequent slides, where the displacement, the direction of a servo motor is done with the help of a pulse, pulse width of the pulse. Similarly, in case of a stepper motor, where it's a combination of the pattern, right? The displacement, the speed is controlled. However, in case of a DC motor, it is the amount of current which is passing through the coil is controlling the speed and the direction of the motor. So, in principle, in construction, in, in terms of controlling, yes, undoubtedly there is a difference in types of motors which are used in robotic applications. However, they also have some limitations. One of the limitation is, let's say, for example, if you look at the pneumatic and hydraulic control systems, they might not be accurate. However, the amount of load they can lift, right? They could be in tons of weight they can lift. Like you have seen the in the some of the videos in robotic videos, lifting the cars, right? Lifting the some industrial machines. They're all done with the help of pneumatic and hydraulic control systems. However, if we use these DC motors, servo motors, stepper motors, they have the advantage of controlling linearly. That means the amount of current which is passing through or the size of the pulse you are generating, there is a correlation exists between the input and the output. And again, you can have a feedback saying that this is my desired value. However, this is my actual measured value. And since there is a difference of percentage of error between the desired value and the measured value, let it be controlled, the remaining portion of the error, so that till the error becomes zero, the system is closely controlling, closely monitoring. So that is possible by using some of the motors. And also I was telling about the displacement part. How accurately I can make a displacement, by how many degrees angular displacement I can make. So again, that is also depends. So feedback, displacement, in short, accuracy, and the amount of load, that's a torque. These are all some parameters you have to consider while choosing the right robotic motor. Sometimes you also have some issues. The issues are their size, their weight. Say, for example, if you are planning for a moving object, moving robot, then you also have a problem of the motor's size, motor's weight, because that itself will become a constraint for you because they are heavy in size in terms of their dimensions, weight. Then, probably for a moving object, lifting the motors itself will become a challenge. The other challenge is in terms of the maintenance. If you look at the pneumatic and hydraulic control system, there are a lot of maintenance issues. Maintenance is a really challenge. However, if you look at the DC motors, there is no maintenance issue. But however, their limitations, their cost is a problem. So you have to carefully look at what is your application and what are the specifications of your the end product which you are looking for. Accordingly, you have to choose the right robotic motor. This itself is a very interesting subject because it's all about electromechanical things. So if you look at the classical motors, generally we classify them as a AC motors, DC motors and some special types of motors. AC motors, like they are called induction motors, synchronous motors, commutator motor, wound rotor motors, squirrel cage motors. So they're all these motors based on their stator and rotor design. They are controlled by controlling the AC, right? They may be 230 volts, say for example, the sinusoidal voltage and current. When you are applying to this right stator, the speed, the direction of that motor is all controlled by the AC signal itself. So the speed and direction is indirectly you are controlling the sinusoidal waveform. However, in case of a DC motors are shunt, series, PMDC, compound, separately excited. So these motors where you are controlling the DC voltage and DC current. So there is a advantage and disadvantage, right? Historically, people felt controlling the DC motor is much easier than the controlling the AC motors. That is the reason why most of the vehicles earlier, right, like for example, uh, local trains, metros, they were all AC motors historically. Sorry, DC motors historically. 70, 80 years, entire country has used the DC motors. But it's a challenge having a DC supply and maintenance, maintaining the DC motors, their size, their weight. These are all some problems. But since speed control is an issue, direction control an issue, designing a electronic circuit to control these motors is easier. That's the reason several years people have used DC motors. However, last 5 to 10 years, entire country, everywhere, entire world is replacing DC motors with AC motors. So now even the metros, local trains, even lift, all of them, right, are your washing machines. They're all are air conditioners, refrigerators. They're all AC motors, not the DC motors. The reason is now the technology is so advanced, your CPU are so advanced, and the drivers, that's a MOSFETs, IGBTs, they are so advanced, right? That converting the energy AC to DC, DC to AC, and generating the desired signals is not a big problem because of this advancement in the semiconductor technologies, people prefer AC motors. So it's no more a challenge in controlling the AC motors. Because of the maintenance issues, now they have discontinued DC motors. However, now when it comes to uh, electrical vehicles, two-wheelers, four-wheelers, and drones, right, or the robots, still we are using DC motors because they are operated on a battery, right, a DC battery or solar panels like that. So since your source itself is a DC battery operated systems or solar panel operated systems, and speed control is anyhow it is not a big challenge, people are still using in such type of applications DC motors. There are some special motors, they are specially designed to operate like stepper motors, brushless. Brushless means that's a drawback actually in DC motor, but now you get a brushless motors, servo motors, universal motors, and so on. So these motors are specially designed, though they are DC motors, but you cannot directly apply the DC. The way in DC motor, what happens? You directly apply the DC supply across the uh, coil. But here, if you give DC, it won't start working. You have to give some pattern of pulses or some combination is there. So that you have to do that. So specially motors. In short, interfacing programming is slightly complicated in special motors that we will see. So the classification of the motors, DC machines, what you can see is how you are connected the field coil. Are you this armature? What is armature? Armature is the one which is a rotating part where some electromechanical thing has some coil, right? Some mechanical joint, energy into mechanical energy. So that's about the DC motors where this field coil, how it is connected. Are you separately exciting with the help of external source, or you have connected that coil in series to your armature, or have you connected this field winding in parallel to your armature, or long shunt. Long shunt means, as you can see, the complete coil is across the armature, or maybe a partial only across the armature, and is how you have connected. There is a basic difference in terms of the interface between the field coil and the armature. So accordingly, they are classified as far as the construction is concerned. How do we control the speed? In case of a DC motor, whatever is the potential you are applying across the motor need to be controlled. If you are giving 100% desired voltage, then the motor will rotate with full speed, or if you are controlling the amount of power which you have delivered to this motor, then the speed you are controlling. Say for example, look at there is a battery DC supply. Instead of directly connecting to the motor, what you are doing is you have connected a series, some transistor. Now, this transistor, the amount of current passing through from collector to emitter, collector is connected to the power supply, emitter is connected to the motor, base is controlling the amount of current passing from collector to emitter. Now, the base, how it is controlling? It is controlling with the help of some variable resistor, and this variable resistor is connected across the power supply. So in short, by moving this knob, what you are trying to do is this variable DC you are applying across the motor. So that is how you are in short indirectly controlling the speed of the motor. The other technique is instead of using that variable resistor, which is a challenge, having that kind of the power control. You generate a pulse in such a way that the on time and off time of the transistor you are controlling, right? For instead of applying 100% DC, you are applying, let's say, 75% on, 25% off, like that. So that means 75% time, 100% DC, 25% is 0% DC supply you are applying to the motor. So in short, what you are trying to do is average DC. So average DC is not 100% or 0%, somewhere between 0 to 100%. So by controlling the width of the pulse, you are controlling the amount of power delivered to the motor. In short, that is controlling the speed of the motor. Let us look at the closed loop control system. Closed loop means it's not that whatever is the desired value, in order to achieve that, you generate the pulse on time and off time. But what is the guarantee that whatever you have generated will give you corresponding displacement due to overloading or maybe due to some errors, right? Losses in the system. There is a possibility that whatever is your desired value might not be at the output. So that's the reason most of the systems are closed loop in nature. What is closed loop here? You have connected a motor across a transistor. You generate a PWM signal so that whatever is the voltage you are applying to the motor, on time and off time, you are controlling by adjusting the width of the pulse. However, with the help of some speed sensor, whatever the speed you would like to achieve, like a tachometer, optocoupler, you take the feedback, that is called measured speed, and you compare with the desired speed. So subtract the desired speed from the measured speed, and whatever is the error is there, that will again adjust the PWM on time and off time in such a way that the speed is further controlled. So till the reference value and the measured value, the difference is zero, this adjustment, either positive adjustment or negative adjustment of the pulse width, will takes place. So if you look at, say for example, if your DC motor is working on 12 volts, V in is 12 volts, and 0% duty cycle, that means completely off, the transistor is completely in off state. So what is the output voltage you apply to the motor is 0 volts. So in return, the motor is completely in off state. Instead of that, the transistor, what you do is only 25% of the time you make it on, and 75% of the time you make it off. And if you apply this voltage, this kind of a voltage where 25% of the time it is at 12 volts, 75% of the time it is at 0 volts. So if this signal is applied to the motor, then on an average what it will get is around 3 volts. So that means now the speed of the motor is around 25% of the full speed. Let's say you 50% of the time you make it on, 50% of the time you make it off. So average DC the motor will get is 6 volts. Similarly, 75% of the time if you make it on, 25% of the time you make it off, exactly opposite to the second case. Then the motor voltage applied is 9 volts. Maybe it will achieve 75% of the speed. If you say 100% on, 0% off, means exactly opposite to the first case. Then the applied voltage to the motor is 12 volts and the motor will rotate with the full speed. So this is what we are saying about pulse width modulation. So you are adjusting the pulse width in such a way that the speed of the motor you are controlling, on time and off time of the pulse you are controlling. So let us look at how to change the direction of the motor. If you apply a positive terminal to positive terminal of the motor, negative terminal to the negative terminal of the motor, then the current will flow in, let's say, positive to negative in this direction. The motor also will rotate, let's say, in clockwise direction. Instead of that, the same DC motor, you reverse it. You connect the positive terminal of the motor to the negative terminal of the battery and negative terminal to the positive terminal of the battery. Naturally, the current will flow from positive to negative in a opposite direction, and you will notice even the motor also started rotating in the counterclockwise direction, reverse direction. So in short, if at all if you want to change the direction of the motor, then you have to reverse the polarity of the supply which you connected to the motor. Okay, so how to achieve this? If you use only one transistor, like we have discussed here, if you use only one transistor and connect the motor in series to the transistor, then you cannot reverse the polarity. You can only adjust the speed, make it on, make it off, or you can make it 50% on, 50% off, whatever. But however, the motor will rotate in only one direction. It won't rotate in the reverse direction. So if you want to achieve that, then you require at least 4 transistors, what we call as a bridge, H bridge. So it looks like H. So where do you connect the motor? You can see you are connecting at these ends. That is collector of these two transistors and collector of these two transistors. Between these transistors, you are connecting the motor. So at least 4 transistors are required if you want to reverse the direction of the motor. Means the polarity which you are applying, positive, negative or negative, positive, if you want to reverse it, then you require 4 transistors where VCC is applied here between these two emitters and ground is connected between these two emitters. Let's see how it works. If you switch on Q1 and Q4, right, means on, Q2 and Q3 off, right? You can see the switches. This is closed, this is closed, this is open, this is open. So this transistor is on, this transistor is off. Then the current will flow from positive to like this through the motor and then back to the ground. So that means current is going in one direction. Motor will start rotating in one direction, let's say clockwise. If you want to reverse the direction of the motor, then you do exactly opposite case. That is, earlier your these two transistors are off. Now you make this transistor on, and this transistor off. I think there is a mistake in this figure. So you reverse it. Then the current will start flowing because the two transistors are closed. The current is started flowing in the opposite direction. Then the motor also started rotating in the counterclockwise direction. So when Q1, Q4 transistors are on, motor will rotate in a clockwise direction. When Q2 and Q4, sorry, Q3 is on, motor will rotate in an anti-clockwise direction. So H bridge is required if you want to change the direction of the motor. However, if you want to only control the speed of the motor, even one transistor is enough. Like in this figure, one transistor is enough to control the speed of the motor. Okay, so we get some integrated circuits called L293D IC, where this IC has the ability to interface to drive two motors. So it has four pins, four inputs, in 1, in 2, in 3, in 4, and four outputs, out 1, out 2, out 3, out 4. And the entire IC works on two supplies. One is 5 volts, second is 12 volts. So this 12 volts is actually PWM signal which is applied to the motor, and the 5 volts is the one which is connected to the circuit of the motor. This is a driver circuit inside the motor. Inside the driver. So when this is how the connections are. As you can see, four ground pins and VCC and two VCCs. One you can apply 12 volts or whatever you want. Second is 5 volts. Where do you connect the motors? On out 1, out 2. You connect one motor. Out 3, out 4, you connect the another motor. And where will you connect the microcontroller? In 1, in 2, in 3, in 4. On these 4 pins, connect the microcontroller pins. So if in 1 is 1, in 2 is 0, if you apply the signals like that in binary form, or in voltage you can say 0 and 5 volts, then the motor will start rotating in one direction. And instead of that, in 1 you make it 0 and in 2 make it you 5 volts, the motor will rotate in the anti-clockwise direction. Similarly, you have two more inputs, in 3 and in 4. If this is 0, this is, let's say, 5 volts, second motor will rotate in clockwise direction. Or if you apply this is 1 and this is 0, the motor will start rotating in counterclockwise direction. And the enable 1, enable 2 are connected to VCC. However, instead of that, if this enable 1, enable 2 also, if you generate a PWM signal here, then the speed of the motor can be controlled. So if you use this IC L293D, you can connect two DC motors for driving, because microcontroller directly cannot drive. Microcontroller can give only 10 milliamperes of current, and that to 3.3 volts or 5 volts. So in order to give 12 volts and that to at least half a ampere, 1 ampere of current, you require a IC like this. So microcontroller is connected to this IC and the output of this driver IC is connected to the motors. So this is called motor drivers because no microcontroller can directly drive the motors. So you require this called H bridge circuit. And since this bridge has ability to drive two motors, so you require four pins for interfacing to microcontroller. So in QU board, right, if you in the output components, if you select the DC motor, right, once you drag it and drop it the DC motor, then the DC motor will give you two options. Do you want left motor or right motor, right? If you, let's say for example, you have selected left motor, then how many options it is giving? Turn left, turn right, move forward, move backward, right? These are left motor forward, left motor backward, like that. So you are given, one is the selection of the motor, Second is the speed of the motor, in which direction you want to rotate. And as far as the speed attribute is concerned, it will give you the number from where 0 to 10, right? Based on the RPM, revolutions per minute, right? Let's say 60 RPM or whatever. So based on the speed of the motor, it is divided in the scale of 0 to 10. So if you select 0, let's say off, 1, 2, 3, 4, accordingly, the speed means PWM, pulse width modulation, will change. And as far as the selection of the motor is concerned, what do you want to do, right? You want to left turn, right turn, right? Move forward, move backward. So these are all, in short, making on and off of the motor. So if you write a program, right, select the component DC motor, drag it and drop it between start and end, and change the attributes. Let's say left motor forward, speed of 5, right motor forward, speed of 10, and be there for 60 seconds and stop both the motors by speed you have selected 0. What does it mean? It means if you are rotating the left motor with 5 speed, right motor with 10 speed, that means both the motors are having a different speed. So it will, the effect will be your robot will rotate in a anti-clockwise direction for 60 seconds. So whether you want to move the motor, right, forward, backward, left turn, right turn, this is all adjusted with the help of on time, off time, and the speed. So you should try all the possible combinations to verify how the PWM pulse is controlling the speed, and then off time and off time, direction and the speed, how you can control with the help of the delay, and the attributes of the component. All right, so multiple examples, I believe you should try it. Let's see some examples. In this example, you have selected only one motor, first example, and if you see the attributes, move forward, right? The motor, your motor, whatever the motor you have selected, move forward and with a speed, full speed of 10, and then do nothing after that infinite loop. So download the program, observe that only one DC motor will move forward with a speed of 10. So in short, what does it mean? Other motor is off. So naturally, it will won't go forward. It will be in a clockwise direction. It will start rotating. Let's look at the second example. It is now this time you say right motor forward with a speed of 10. You just verify whether right motor is moving forward direction or not with a full speed of 10. This is the second example. In the third example, you have selected both the motors, left motor forward with a speed of 8, then after some delay of 2 seconds, then right motor backward with a speed of 5, and after that your program is in the infinite loop, means do nothing. So notice that with a delay of 2 seconds, one motor will go forward with the 8, with a speed of on the scale of 8, and other motor will start rotating backward with a speed of 5. This is the third example. In this program, first of all, the program is in the while loop, means infinite loop, because while 1 means true. Then when it enter into the program in the infinite loop, you have selected motor, left motor forward with speed of 5, right motor backward with a speed of 10. So both the motors have different speeds. One is going forward left motor, right motor is also forward. And after a delay of 4 seconds, you said stop both the motors, and then further delay is there. But however, since it is a while one, means true, infinite loop, so this behavior will be keep on happening again and again and again. So try it and see whether this loop infinite number of times that two motors with different speeds forward with a delay, both of them will be stopped. Again after 2 seconds, this behavior should be repeated. This is example number 4. And the fifth example is again same. The program is in the infinite loop, and in the infinite loop, true, first you have selected motor 1, forward with a full speed, after delay, move backward with a full speed, delay, turn left with a speed of 10, delay, turn right with a speed of 10, delay. And this behavior will be repeated again and again. In the sixth example, now you are using conditional statements, switch statements. Since your board is having some switches, on off, press to on switch, so this condition, if switch 1 is pressed, then this motor will go forward with a speed of 10. Else if switch 2 is pressed, then the motor turn left with a speed of 10. Else if switch 3 is pressed, turn right with a speed of 10. Else stop all the motors and end if the statement. And after some delay, since it is an infinite loop, this program will be executed again and again. Means the switch 1, if it is pressed, if the condition is satisfied, if switch 1 is pressed, move forward with speed of 10. Switch 2 is pressed, turn left with a speed of 10. Switch 3 is pressed, turn right with a speed of 10. If none of the conditions are satisfied, you are say else motor should be stopped and terminate the end if statement. After 20 milliseconds of delay, this again will start reading the switches. So these are all conditional statements where if the condition is satisfied, then only the action will takes place. This is example number 6. Example number 7 is a combination of motors and LEDs, where in the while loop, infinite loop, you are saying motor, right motor with a speed of 0, LED 2 off, then left motor with a speed of 8, then delay, then left motor with a speed of 0, LED 1 off, right motor with a speed of 8, LED 2 on with a delay 2 seconds, then move forward speed of 8, LED 1 on, then LED 2 on 2 seconds delay, and this behavior will be repeated again and again. So this is in short mixing various output components. Maybe you can also add buzzer, right, like that. So multiple components could be part of your program. This is example number 7. Example number 8 is again a conditional statement, right? The conditional statement this time is different. It's an interesting thing. It's not about the pressing the switches. This time you are reading the infrared sensor. So you have a sensor, infrared sensor on your PCB, which is front center infrared sensor. If any obstacle, right, it will verify, look for one. Then move forward if there is no obstacle. If there is no obstacle in the left side, turn left. And if there is no obstacle on the right, turn right. Else, stop the motors. So instead of reading the switches in the conditional statement, this time we are looking for infrared sensor. Three sensors are there in front side of the vehicle: front center, front left, front right. And after downloading the program, if try to right obstacle put some obstacle and see whether the behavior of the motors is changing or not. This is example 8. Example number 9. First, between the start and end statement, the first motor will move forward with a speed of 10. Then in the while, this time it's not while 1. It's not infinite loop. It's a conditional statement where saying that some motor count, right? You are counting the motor, right motor, left motor, 100 times. So as long as this count is not satisfied, this loop will be executed. If the count is satisfied, it will come out of the loop and LED 1 will be on, and it will terminate the program with 3 beeps. So what does it mean? It means that once it enter into the loop, then now it is continuously looking for which count your left motor. So in the back side, there is a encoder, infrared sensor is there, so that whenever the wheel is moving, right, that's the reason why we started moving the vehicle in forward direction. So whenever that sensor, right, left motor count is greater than or equal to 100, then this condition will be satisfied. And if this is terminated, again, if the motor, which this time right side of the motor greater than or equal to 100, then this condition will be satisfied with a speed stop, means in both the cases you want to stop. And if, and then there is another conditional statement where you are looking for the count of the left motor and right motor. If this condition is not satisfied, this will be executed. If the condition is satisfied, it will terminate the loop, LED 1 will be on, and program will be terminated. So now you verify whether two motors, left motor, right motor, based on the how much distance it has traveled, there is a counter, because the backside wheel, it has some optocoupler, right? It is cutting the light, and how many rotations it has rotated, it will count it, and it is looking for a counter value of 100. So you can also change this variable up to 255 and see how much distance the vehicle has traveled. This is another interesting feature of counting the number of revolutions of the wheel itself, left wheel and right wheel. Example number 9. In example number 10, it's an infinite loop. First of all, you enter into the loop. Then when it enter into the loop, you have defined which variable, infrared variable. Now this is an interesting thing. So this time this infrared variable is coming from your TV remote, right? You have a remote control. So with the help of the remote control, now you press the switches. Every switch has some code, as you can see, for example, 32, right? 33, 16, 17, like that. So based on that, right, whichever is the key on your TV remote you have pressed, right, because you are verifying IR, if IR value is 32, then this motor will go forward, move, move forward with a speed of 10. Else, if this time you are looking for which condition, if the IR value is 33, move backward. Else if your TV remote you have pressed a button of turn left, sorry, turn right, then it will start moving right direction with a speed of 10. If you have pressed the turn left button, then the value will be 17. This condition will be executed. Turn left with a speed of 10. Else all the motors will be stopped. And since it is an infinite loop, unless you press the button on your TV remote, right, forward, backward, left, right, your vehicle won't move because it's continuously reading the sensor value of the TV remote, right? And then accordingly, if this condition is satisfied, then only the motor displacement, right, motor movement takes place. So this is another classical example of how to control a robot with the help of a remote, infrared remote. All right, so these are various types of programs related to the motor. Again, let's see, where these sensors are. If you recollect, right, there is a sensor here, that is a ninth. There is a sensor here, 10th. So whenever this wheel is moving, rotating, this sensor will cut the light because you can see there is a hole on the wheel. It will cut the light. So this is what we are saying counter value of the left wheel, counter value of the right wheel. So the 10th program is about the TV remote. So here you can see the 14th. There is another sensor. You can see the remote. So this remote button, when you press it and focus that the transmitter towards the TV remote sensor, which is there on the back side of the wheel. Then if you press left button, right button, forward, backward, accordingly these two wheels will start rotating. In another example, we were looking for these front sensors, front center, front left, front right, whenever some obstacle comes, right? This is not counting. This is only presence and absence of a obstacle. However, this ninth and 10th, these are the counters, right? They are counting how many times the wheel has rotated. So three sensors you can use in this example, not only just moving the vehicle forward, backward, left, right, or you can also, right, follow some this thing, but you can also look for these sensors, forward sensors, backward sensors, or a TV remote sensor. Other than these two DC motors, there are few more motors, though they are not provided on the board. However, just for understanding, let us discuss two more motors. One is called servo motor. As we have discussed in the types of motors, servo motor, you can see it is a 3-pin connector. Orange where you have to give the pulse. Red is supply, let's say 5 volts. Brown is ground. So this orange pin, right, wherever you see orange wire, the kind of pulse you have to give is a pulse width modulated signal. In case of a DC motor, we have seen two techniques. One is either you control the current or you control the width of the pulse. However, servo motor purely works based on the pulse. Let's say the pulse is of total duration of the pulse is 1 millisecond, then it is at 0 degrees. If you apply, let's say 1.5 milliseconds of the pulse, then the motor will move to 90 degrees. If you apply a pulse of, let's say 2 milliseconds, the motor will move to 180 degrees. So between one pulse to the other pulse, at least 20 milliseconds gap has to be there, delay has to be there. So this is how a servo motor works. So the servo motor speed, the servo motor direction, everything is based on the width of the pulse, right? The width. Generally, the motors which are used for hobby kits, they are used this kind of a width. 1 millisecond for 0 degrees, 1.5 for 90 degrees, 2 milliseconds for 180 degrees. And if you want to change the direction, then again you instead of 1 millisecond pulse, you have to change to 2 milliseconds pulse. What kind of hardware is there inside this servo motor? You can see some gears are there. So there is a control board is there inside the motor, and there is a reference voltage is there called potentiometer. So whenever you apply a pulse, this control pulse is applied right to the motor. The motor will start rotating based on the clockwise or anti-clockwise, and correspondingly there is a potentiometer also rotates. So it will be a feedback that you have given some pulse, it will make some displacement, and then the potentiometer also rotates. Whatever is the desired value, whatever is the measured value, if there is any percentage of error, again the motor will rotate till that error becomes zero. So what we are doing is the closed loop control system is inbuilt inside the servo motor itself, this entire circuit. You don't need to have a separate sensor externally like in DC motor. I was telling you have to measure the displacement, but here the displacement is automatically measured by the motor itself. That's the beauty of servo motor for accurate positioning, since it has an inbuilt sensor. Second is easy to control because what you are trying to give is a pulse, and the width of the pulse you are controlling, so that the displacement indirectly you are controlling, and the direction. So they have a inside the motor itself, this a geared mechanism is there, and plus the potentiometer is also inbuilt, and there is a circuit. What we give is only a pulse and VCC ground. This entire feedback, right, closed loop control system, controller, motor, gears, positioning sensor, everything is inbuilt. Whatever is the signal you give, it will also not only control, it also take a feedback till the position of this, right, the your uh, motor is adjusted. This loop is taking care of the making the error zero, right? So like I was saying, if you look at the pulse pattern with the interval of 20 milliseconds, so 50 hertz, the speed you can achieve, because between one pulse to other pulse, the delay involved is 20 milliseconds. So 1 milliseconds means zero point 0.5 milliseconds at 0 degrees. 1.5 milliseconds will give you a displacement of 90 degrees, and 2 milliseconds will give you a displacement of 180 degrees. The another DC motor, special type of motor, is called stepper motor. In stepper motor, the number of windings are 5. Not in earlier case we have seen there is only one winding. In DC motor, two windings. Servo motor only one input. But however, in stepper motor, you can see 1, 2, 3, 4, 5. So 5 pin connector. They are available with different voltage ratings, but we are using currently either 5 volts or 12 volts stepper motors. Since the number of phases are 4, it is called as a 4 phases. The fifth one is a common point. You can see this center tap is connected common, where the supply, positive supply is applied here on pin number 5. Otherwise, actual phases are 1, 2, 3 and 4. So 4 inputs, one common point. Your red is common point. 4 inputs. And based on the type of motor, you can have the speed, right, speed angle, how many revolutions you want, and per revolution how many steps are there, and what is the step angle. Everything is based on the construction of the motor. Okay, so if you want to interface to your board. So you should remember you require a driver IC because again the motor draws huge amount of current. So you require like at least a IC like we have discussed uh, L293D or ULN200 IC where 4 inputs and 4 outputs. The fifth one is common, red is common. So you can see the color code also. First is orange, then yellow, then pink, then blue. So in one, if you connect the microcontroller in one, then it goes to the blue. Then in two, signal should be applied to pink. In three is applied to yellow. In four is applied to orange. And the red is common. Common means the 12 volts is applied to the red wire or 5 volts based on the rating. So you have to energize. There is a pattern. You have to energize in such a way that, let's say, when 1 is on, 2 is off, 3 is off, 4 is off. When 2 is on, 1 is off, 3 is off, 4 is off. When 3 is on, 1 is off, 2 is off, 4 is off. When 4 is on, 1, 2, 3 is off. So based on the pattern, right, which winding is energized at a time and other three windings are off, accordingly the stepper motor will make a step. So what is the step? That depends on the inside construction, how many windings are there inside the motor, so that it will make a corresponding displacement. Let's say for example, you have a 1.8 degrees is the step. That means 360 degrees is one revolution divided by 1.8 degrees. That means you require 200 steps. Means 200 times you have to give, let's say 1000, then 0100, then 0010, then 0001. So like that, 200 times if you give that pattern, then it will complete one revolution. So one step, right, is done by one winding. Second step, second wind. Third step. So that means 200 steps means 200 divided by 4, right? That means 50 combinations. So 50 times this loop has to be completed. Then 50 into 4, 200 steps. If you give, then the motor will rotate in one complete revolution. The same pattern, if you reverse it means what? Instead of giving first blue color 1 remaining 0, you say the in 4 you make it 1, means this orange color you make it 1, other 0 0, then it will make a step in the opposite direction. Then make yellow on and orange off, pink off, blue off. It will make the second step in reverse direction. So like that you reverse the pulses, then the motor will start rotating in the opposite direction. All right, so these are some calculations. If you use this stepper motor, just now I have shown, which has a stride angle of 5.625 divided by 64 in a half step mode. So this means that the motor has a step angle of 5.625 degrees as a displacement. So 360 degrees divided by 5.625 will give you 64 steps in a half step mode. In full step mode, 64 by 2, that is 32 steps. So what do you mean by half step and full step? That means the pulse combination which I had given, instead of energizing one winding at a time, because one winding at a time means you will have only 4 combinations. If you energize 2 windings at a time, then you will have 8 combinations. So that's why do you want to make a half step or full step? Accordingly, those many combinations you get. And internally, the output shaft is driven by a gear. There is a gear is there, so that if you let's say 1 is to 64 is the reduction. This means that the shaft which is visible outside will complete rotation if the motor inside rotates 64 times, because the gears, right, is arranged in such a time. Internally if it rotates 64 times, externally the shaft will make a one step. This means that the motor will have to move 32 into 64 times, right? That is 2048 steps for the shaft to complete one full rotation. This means that you have to write a program for a 360 divided by 2048 to get a 0.18 per step. This is what I was trying to tell, that the construction of the motor is in such a way that internal organization, gear ratio, winding placement is in such a way that the if you give one pattern, it will make one step. And such type of steps, if you give 2048, then 360 divided by 30, the displacement will come out to be per step means 0.18 degrees is the displacement. That means how accurately you can make a step. That is the key point here, why people prefer stepper motor. So we have discussed, though QU board doesn't have servo motor and stepper motor, but just for understanding, if at all if you want to interface externally, you can do that. But separately you have to write a program. But maybe in due course, our other systems have this provision for interfacing stepper motors and servo motors. If you want to use the other softwares, right, like in due course, so then you have to also use some libraries for connecting the stepper motor and writing the programs. Because finally, the I was telling about the combination, right? If you want to give the half step, full step, and the forward direction, reverse direction, the pulses is not one. Here, the pulses are at least four pulse pattern it is to make a one step. So that is the combination. If you do full step, then four possibilities. If you do half step, you have eight possibilities of rotating the motor. And based on the internal gear ratio, like it is said, 1 is to 64, then those many pulses if you give, it will complete one revolution. So that's the bit construction of a motor. All right, so these are at least the basic motors which are used in robotic applications. For what we have seen is a DC motor, which is good, but then control is good, direction is good. However, there is no feedback. In case of a servo motor, it has an inbuilt feedback. It's really good for displacement because you are controlling the pulse width. So for accuracy point of view, it's good. Third, you have a stepper motor, but it's not for heavy loads. But if you want to make a step, let's say 0.8 degree, 0.18 degrees like that, then for step movement, these stepper motors are good. So based on the application, you have to wisely choose which motor is suitable for your application. All right, that's all for this session.